Hi, today I'm going to talk about optimal substructure, and this is going to be a bit of a long video because I'm not too sure how to cut it into small pieces. You see, I'm not going to start with optimal substructure right away. I'm actually going to talk about divide and conquer first. So maybe if you want to, you can take a break when I'm finished with this part. But this is something that you already know well anyway, so I hope this is going to be easy, the divide and conquer part anyway. We're going to talk more about this in week 6, but that will be about something else. I'm not going to talk about, I'm not going to reintroduce divide and conquer in week 6. We're just going to talk about recurrence relationships when it comes to week 6 to find the complexity of the algorithm. But again, this is something that you've done in the first year even. The idea is that you got a problem, you divide it into small subproblems. This is something that we've been doing for the last few weeks as well. When we draw the search space, when we draw the tree, and then we conquer the subproblems, and then we combine the solution to the subproblems to generate the solution to the original problem. So the classical example here is merge sort, which I hope you remember how to do from COM 25, COM 2010. If not, just look it up. It's nothing hard at all. Okay. The most important aspect about divide and conquer that I need you to know is that you are applying the same algorithm to compute the subproblems, right? So you can think of like starting fresh. You know, it's exactly the same problem with different set of inputs. Like that's what happened when you conquer the subproblems. Like you did that by using a loop, using a recursion, the same thing, right? The same problem, same algorithm, different set of inputs. When we first start talking about dynamic programming, we talk about the Fibonacci algorithm. And what do you think? Do you think Fibonacci is a divide and conquer algorithm? I mean, if I want to work out Fibonacci of n, I have to work out Fibonacci of n minus 1 and Fibonacci of n minus 2 separately, right? Of course, we know that we can use dynamic programming, but just the problem itself, if you have to work out Fibonacci n, you need to work out Fibonacci n minus 1 and Fibonacci n minus 2. So you are kind of dividing the problem into 2 small bits. You conquer them separately and then you combine them again. Now the other question someone asked, is boundary search a divide and conquer algorithm? What about finding the largest element? I give you an array and I ask you what's the largest element inside the array. Is that a divide and conquer algorithm? The thing is, when students think about divide and conquer algorithm, they normally think about recursion. Oh, if it's recursion, then I can do divide and conquer. If it's just a loop, then it's not really divide and conquer. But if I can write something as a loop, I can also write it using recursion, right? So boundary search, I'm not sure if you did boundary search using recursion, but finding the largest element, definitely sure you're not using recursion, right? You're probably doing a for loop. But I can also find the largest element using recursion, like as so, right? If I have to find the largest element from the array index 0 up to array index n, say, then I can split that into 2 parts. I'm going to look at the element 0, like the first element, and then I'm going to find the largest one from index 1 to index n. And then I'm going to compare the two, see which one's biggest. However, boundary search as recursive function probably makes a lot more sense, right? So we're going to start with that. We're going to see if boundary search is divide and conquer algorithm. So here we are, boundary search. You start with the whole array in the beginning, and then you look at the middle element, and as soon as you see the middle element, you can discard 1/2 of it. Right? And then you keep on doing the same thing. So again, it's the same problem. You look at the middle element, and then you discard 1/2 of the array. Again, keep on discarding 1/2. So some people argue that this is not divide and conquer because you're not actually going to the 2 different branches. Remember that the divide and conquer means I have to divide the problem into small subproblems and then have to combine the solutions. And here, I don't actually go to the other subproblem. So I've seen people say this is discard and conquer, not divide and conquer. But it's the same idea, right? You have a array, you go left and right. Well, you can go left and you can go right, but here you decide that, well, I don't need to go to the left hand side, so I just go on the right hand side. To me, this is divide and conquer. Finding the largest element is similar as well. So I can divide the array into two parts. The one on the left, just one element, and the one on the right. I'm applying my algorithm again to find the largest element. If there's only one element, then, well, that element must be the largest element, right? But if there isn't, then I can keep on recursively find the largest element, like so. So here's the code that I have for finding the largest element. If you look at the first code here, what am I doing? I'm given an array A. I have integer I, integer j, which I'm guessing just the left index and the right index, like which part of the array I'm looking for. And max here is just the max element I have so far. Okay, so if at any point I is greater than j, then we're done. Well, that's an empty array, so there's nothing to return. Otherwise, if the element I'm looking at is, well, the first element, the I, the leftmost element is bigger than max, then max is the biggest element. That's what we do when we have a loop as well. And then what do I return? When I combine the solution, I return the maximum of the max, what I have so far, and I recurse starting from index I plus 1. I'll also send down max over there. You can do this differently, and that's what I have down here. Can you imagine that this is a bit more like a boundary search where you look at the middle of the array? So I'm going to look at the middle part of the array every time, and then I'm going to see is that bigger than the maximum element I have so far. If it's not, then I'll look at the left side of the array. Well, actually, sorry. At any case, I will look at the left side of the array, and I will look at the right side of the array. Now I'll compare the largest element in those arrays with, well, in those subarrays with what I have so far, max. So the tree is going to look slightly different now. Instead of having the left subproblem with the subarray just size 1 and the right subproblem with the subarray size n-1, now I have two subproblems of equally the same size, well, roughly the same size, right? From 0 to n/2 up to n/2 plus 1 to n. So the left subarray and the right subarray about the same size. By the way, if you've never coded something like this before, give it a try. I mean, I know you can do this easily using a for loop, but try implementing it using recursive function. It is pretty silly, but it's good practice for you, like to understand how to write a solution using recursion. Because when you write a solution using recursion, it really feels like you're starting fresh with a new problem. So you can really appreciate the whole problem versus subproblem being the same, like what I mentioned earlier. Okay, and also, why am I talking about this again? Why am I talking about divide and conquer? Because I want to see that, I want you to see that divide and conquer and dynamic programming, they're kind of very similar, right? What do you do in dynamic programming? You got a problem, you break it down into small subproblems, and then you recombine them. It's the same thing. So when you look at these three problems here, can you apply dynamic programming in all of them? Well, Fibonacci, sure, you can apply dynamic programming. But boundary search, how do you apply dynamic programming? Do you have overlapping subproblems with boundary search? You shouldn't, right? Because you're just looking for an element, then, well, first of all, this is, as we saw before, this is like something like discard and conquer. So if you go to one branch of the tree, you don't care about the other branch. You only go to one half. But what about find largest? Can you do dynamic programming here? You probably can, but you wouldn't. Generally, no. You want to dynamic programming here. In fact, this one here you probably write using a loop. But think about that. Think about divide and conquer versus dynamic programming. Make sure the division is clear in your mind, because dynamic programming requires requires a problem to have overlapping subproblems. So I would say that dynamic programming is a divide and conquer approach. Just that you don't really apply it on every problem. Most of the time we use dynamic programming for optimization problems. We don't use it really for search problems, but can we? How about decision problems? How about counting problems? Remember, these are the 4 problems that I mentioned at the start of the subject and in week 1. That you have optimization, search, decision, and counting problems. So, while yes, dynamic programming is mostly used for optimization, can you use it for the other ones? Let's discuss this using Knapsack as an example. Hopefully you remember Knapsack by now. I've talked about it a lot. So if I give you a set of items, each item has a weight and a value, and also give you a limit L, you got to work out which item you should take, such that the weight is less than L, but you maximize your value. So ask yourself, can you use dynamic programming to solve Knapsack? Well, you can definitely use brute force, but are there overlapping subproblems with Knapsack? So here's a concrete example with items from A to H and a limit of 40. So the tree there is just the brute force method of solving Knapsack, right? So every level you either choose or not choose an element. So level 1, I pick A or I don't pick A. If I pick A, do I pick B? Or I don't pick B? Or do I pick C after I pick A and B? Do I not pick C? And so on. This tree is going to have 2 to the n complexity because that's the number of combinations that we have. And that's just the brute force way of doing Knapsack. Do you see any overlapping subproblems here? Hopefully you can spot that the weight of A and B, if added together, is the same with the weight of C. So at that point, actually, after you pick A and B, you will have 28 units left of weight. And if you pick C, you also have 28 units left. So this subtree and that subtree, at that point forward, you'll be doing the same problem from scratch. Well, imagine you at that point you will have D, E, F, G, H to choose from, right? You will have the same amount of weight left, or same amount of capacity left. Then you'll have different values, sure. But instead of solving the problem twice, you can just do it once. Just imagine that you start with limit equal to 28, and then you ask, here's a knapsack with 5 elements. What's the best I can do with weight equal to 28? So yeah, definitely you can do this using dynamic programming. All right, and this is something that you need to be able to do with. You need to be able to recognize, are there overlapping subproblems? That's one of the points I'm trying to make with this video so far. Like, I'll show you problems where you cannot use dynamic programming, and now here's one where you can use dynamic programming. So you gotta know when you can use dynamic programming and when you can't use dynamic programming. Okay. And yeah, this knapsack here, this is gonna be an optimization problem for knapsack, but I can reword knapsack in different ways. For example, I can make knapsack into a decision problem. Is there a value V with weight under the limit L? That is a yes or no. And think about it. Would your calculation be different to this one? Right? Would you still be doing brute force? What about search problem? Give me all the combinations with value greater than V and weight under limit L. Again, can you come across the same scenario here when you have overlapping subproblems? What about counting? How many combinations are there So don't worry about searching them, don't worry about giving the actual combination, just count how many there are. And all of these problems, you will come across the same overlapping subproblems as the optimization version. So yes, you can use dynamic programming for all of these. Okay. Hopefully now you have an even better idea of dynamic programming, where you can use it, and what you can use it for. Okay, so we've only talked about overlapping subproblems so far. There is one more thing that you need in order to solve something using dynamic programming. You need to have something called optimal substructure. Now, I'm taking this out of CLRS, chapter 15, the textbook. So if you want to, you can read the textbook. If you read the chapter, you'll see pretty much the same thing. Only there'll be a lot more words for you to read. And it's a lot more terse as well. It's a lot more complete, I would say. So generally with these lectures, we're not going to, mathematically anyway, we're not going to the same level of complexity. I place more importance in you understanding dynamic programming, like just the general idea. I don't need you to be mathematically terse, but it's always a good thing if you are. So go have a read on the textbook, see what you think about the textbook. Anyway, optimal substructure, what is it? So this is a property of the problem, not really algorithm, but a property of the problem. So we say that a problem has optimal substructure if the optimal solution to the problem can be constructed using optimal solutions to the subproblems. And you may think that this statement applies only for optimization problems, but this is really just define Conco. Right, so if you are doing define Conco and you kind of like solve the left subtree and solve the right subtree, you are using the same algorithm, right? So if your algorithm returns the most optimal answer, then when you go to the left subtree and you go to the right subtree, remember, it's like you're doing a new problem, then you expect to get the optimal answer as well on both sides. Now, does optimal make sense when you're doing a search problem? Well, no, right? Because you're not trying to find the optimal. If I'm looking for the Fibonacci number, I can't really talk about optimality. But the same concept, I'm applying the same algorithm on the left subtree and the right subtree. So even though they're not optimization problems, it's still the same algorithm. So you can kind of ignore the optimization bit for general dynamic programming. I guess what I'm trying to say here is that the textbook frames dynamic programming as a way to solve optimization problems. And I'm following the textbook, which is why I have this optimal substructure definition. But in general, if you're not solving an optimization problem, then you can say that with dynamic programming, this will only work if the solution to the problem contains solutions to the subproblems. In other words, you can only use dynamic programming if the solution to the subproblems actually matters in constructing the solution to the problem. Now, you may think, when would it not matter? You're going to see later, right? There will be examples where you can't do this. Very rare, but there is. But for now, yeah, just use this definition for optimal substructure. And I'm pretty sure most of the time, I'm pretty sure that when I ask you about dynamic programming, it's going to be about optimization anyway, because that is the most interesting set of problems, optimization. Okay. So, optimal substructure, optimal solution to the problem, and optimal solutions to the subproblems. Let's go back to the knapsack tree. And imagine that I only have 3 levels, right? So just keep it simple. So level 3, you have 4 subproblems here, okay, which you can break down into further subproblems. The question here is just, do I pick C or I don't pick C? And in all 4 cases, we will grab the optimal answer. Well, here optimal meaning the one with the highest value. So every subtree, every problem here, I have 2 options, and I will always take the left one. Well, this is a bit of a not great example. And if I go up further on level 2, again, I have subproblems, and I will pick the optimal solution. And this goes all the way to the top. So the way Knapsack work is that you have a problem, you break it down into small subproblems, and then from these all these solutions to the subproblems, you pick one which is optimal. So you will hope that the solution to the subproblem is also optimal. It probably sounds a bit too obvious, that it's actually sounding silly, but that's really all there is to it, to optimal substructure. So imagine you have the original problem up top here, and you can break it down into subproblem A, B, C, and D. For your original problem, you want the optimal solution from A, B, C, and D. This is what you need. In order to solve the problem, you must have the optimal solutions to all your subproblems. So if, for example, A can have 3 possibilities as an answer, well, let's say you want to maximize the value, right? And A has 3 possibilities, 171, 43, or 89. You expect A, when you solve subproblem A, you expect it to give you back 171. Because if it doesn't, you won't be able to construct your optimal answer. In fact, we're going to show, later on, we're going to prove this in a way. We're going to argue this more formally. All right? But basically, at any given point, I expect to have the optimal solution to my subproblems in order for me to be able to construct an optimal solution for my problem. For example, here, I expect to return 193, not 171. Right? If I was actually returning 171, then I won't have the optimal answer. That's all there is to optimal substructure. Your optimal solution up the top must contain the optimal solutions to the subproblems. Okay, let's think about optimal substructure in terms of other problems that you have seen before, like minimum spanning tree. What is the problem? What is the subproblem? And does it have optimal substructure? See, this is actually a good exercise for you to have. Like, you've seen lots of problems before, and you need to know how to break it down from into problems and subproblems. And you know how to use Prim's algorithm, maybe, to construct a minimum spanning tree. But can you see the problem and the subproblem here? So if I give you a tree with, give you a graph with 10 different nodes. So that's a problem. Here's a graph with 10 different nodes. How do you find the minimum spanning tree? So how do you break it down into small subproblems? So in the case of minimum spanning tree, you just pick one node, all right, and you pick one edge coming out of this node. And which one do you pick? You probably pick the one with the lowest weight, right? You pick the one with the lowest weight, and then you have 9 other nodes remaining, and then you got to find the minimum spanning tree of that 9 nodes. Okay, so the optimal answer will give you the minimum spanning tree. But when you think about it, from that one node I have, right, I'm gonna have to find the spanning tree from the other 9 nodes. If the answer from that subproblem is not optimal, right? If I don't actually get the minimum spanning tree from the other 9 nodes, then I won't be able to give you the minimum spanning tree for the 10 nodes. Does that make sense? Hopefully, yeah. So my optimal solution for the minimum spanning tree with 10 nodes must contain the optimal solution to the minimum spanning tree with just 9 nodes. Same thing with the shortest path. You can think about Dijkstra, for example. The Dijkstra algorithm to find the shortest path from COM25, COM 2010. So let's say I want to find the shortest path from A to Z, right? Then I can't go directly from A to Z, right? So I got to go somewhere else. Either I go to B or I go to C. But in both cases, since I have to go to B before I can get to Z, I must be able to find the shortest path from B to Z. So, or from C to Z. So let's say I call the algorithm again, like on the graph with A remove. If I can't find the shortest path from B to Z, or if I can't find the shortest from C to Z, right, one of these, whichever is better, then I won't be able to give you the shortest path from A to Z. See, the shortest path from A to Z must contain the shortest path, well, either the shortest path from B to Z or the shortest path from C to Z. Like, you decide which one's better, go to B or go to C. But my optimal solution, right, the solution of the shortest path, must contain the optimal solution to the subproblems. And the subproblems are go from B to Z or go from C to Z. What about the harder problems? What about minimum vertex cover? I'll let you think about this yourself, but minimum vertex cover will be similar to Knapsack in a way, because every node, either you choose it or you don't choose it. So you have n nodes, you have 2 to the n combinations. Same thing, like, all right, the first node, will you choose it as a cover or not? Second node, will you choose it or not? And then so on. It does have optimal substructure. Maybe it's hard to see. We can maybe discuss that in workshop about what the optimal substructure is. Traveling salesman actually, I think, is easier to see because it'll be similar to shortest path, right? With traveling salesman, you gotta find the shortest route to visit every city, and then you go back to the original city. So I'm gonna say, like, start with A again. So I gotta go from A to every other city, then I gotta go back to A. So one subproblem is that I can go from A to B and from B to every other city and go back to A. So your subproblem is B goes to every other city and goes back to A. Or because that's not the only one. You have other ones, like if A can go to C, then you can go to C to every other city and go back to A. But again, whatever the answer is, if it's optimal, right? So you can go from A to every other city and A again in the best way. Then that solution must contain the optimal solution of going from B to every other city and go back to A. Or maybe if going from C to every other city and go back to A, or whatever, like whatever A is connected to. Because you will have all these options, you will have the optimal answer to all these subproblems, and then you choose one which is the best. So that is, that means this problem has optimal substructure. Do you also see overlapping subproblems as well when you have traveling salesman? Right, it's kind of similar to shortest route in a way. So yeah, you can see overlapping subproblems. Hopefully, there is overlapping subproblems. Like if you go to A and then to B and then to C, that would be the same as you go to A and then to C and then to B. Right, because that means you've been to all 3 cities, and well, the rest, you just have to visit every other city apart from A, B, and C. So does it mean that you can use dynamic programming to solve traveling salesman? Yeah, it is. But the question is, can you use dynamic programming to make it to solve it efficiently? Because traveling salesman is n factorial. It's not to the n. If you use dynamic programming, you go down to n squared to the n, which is still exponential. So there's an XKCD comic there. And I think one of the learning outcomes from this unit is to increase your understanding of XKCD comics. So, yep, that's there. But anyway, that is optimal substructure. Now, I'm guessing all the problems that you've seen so far has this optimal substructure. Because if you see a problem, right, and you can actually solve it, then you're probably using recursion, you're probably using a loop. That means you can break it down into small subproblems. So if the problem doesn't have the optimal substructure, yeah, well, actually no, that's not quite true, because brute force means you still break it down into small pieces, right? And yeah, there are some problems where you have to use brute force because you can't find a good optimal because it doesn't have the optimal substructure property. But anyway, again, why do you care about the optimal substructure property? Because one, you want to find an optimal solution to the problem, right? And the way we do it is that we break it down into small subproblems, right? Because we can't handle a big problem. You have to break it down into small pieces. And that's good because sometimes we can find overlaps, we can use dynamic programming. And you want to apply the same algorithm to the subproblem. Like I said, like starting fresh. Start within it's like doing a new problem with a different set of inputs. So if my original problem is to find the optimal solution, so my algorithm will find the optimal solution. If I apply the algorithm to the subproblem, I will also get the ultimate solution on the subproblem, right? That's how it makes sense. So you expect that if I have an optimal solution to my problem, it will also have the optimal solution to the subproblem. So hopefully, so far, you've been hearing me talk about optimal substructure, and you think, yeah, that's obvious. How can it be the other way? How can you have, how can your problem, how can your solution to the subproblem not contain the optimal solution? That doesn't make sense. But there are problems with no optimal substructure, although they are a bit rare in my opinion. I had trouble finding one to give you as an example, and even the one that I have here, you can argue that it still does have optimal substructure, but we'll see. So what I mean by not having optimal substructure is that you got a problem, you can break it down into small subproblems, you apply the same algorithm, you get something optimal, but this doesn't actually give you the optimal solution to the original problem. You still break it down in order to solve it. So like brute force, you still break down the problem into small subproblems, but these are sometimes more like counting problems or search problem where you go through everything anyway. You can't really apply dynamic programming on these. So what are they? Now, this is more like an advanced topic. Generally, with dynamic programming, you will only deal with problems with optimal substructure. You have to work out what the optimal substructure is. You have to show why it has optimal substructure, and you got to find the overlapping subproblems. So I'm not going to ask you about problems without optimal substructure. Most likely I won't. So here's one, the longest path problem. I want you to find the longest path between two vertices without visiting any vertices twice, like a simple path. Because if you can visit the same vertex twice, then you can just have a cycle. Like you can go from A to B to A to B to A to B to A to B and so on. Like the longest path will be infinite. So these edges, they are bi-directional edges. You can go from A to B. You can also go from A to B. Oops, I mean, if you can go from A to B, you can also go from B to A. Okay. So, how do you break this down into smaller subproblems? You want to go from A to E, for example? So, one way you can decompose this into small subproblems is by asking, what is the longest path from A to B? And then from there, what is the longest path from B to E? Remember, like, you have the same problem when you break down a problem into a subproblem. It's still the same problem, and you want to be able to use the same algorithm on it. So you first start by asking, what is the longest path from A to E? And then you break it down into small subproblems. What is the longest path from A to B? And what is the longest path from B to E? This is where you see a problem. Because the longest path from A to B is A, C, D, E, B. And the longest path from B to E is B, A, C, D, E. They overlap. So you know the longest path from A to B, and you know the longest path from B to E, doesn't really help you give a solution from the longest path from A to E. You can't combine them. Okay. Now you can probably fix this by changing the question. So you can say instead of finding the longest path, you can say I'll find the longest path from A to E, and you're not allowed to go through some vertices. So when you find the longest path from A to B, you're not allowed to go through A again. And when you find the longest path from B to E, you're also not allowed to go to A. But that would be a slightly different problem. So it's important that you define the problem properly. In this case, if the definition is just find the longest path from A to E, then you will see that there is no optimal substructure. So here's another one. The maximum clique problem. So a clique is a set of vertices which are all adjacent to each other. So you got two cliques here in the graph. You got the purple clique and the green clique. Now the maximum clique problem is asking you to find the clique with the largest number of vertices, which would be the green one there, because that's a clique of size 5. Now even from here I can ask you, what is a sub problem? So you got your clique, well, you got your graph here. Problem is go find the maximum clique. How are you going to break that down into smaller sub problems? Are you just going to take a node away? Like, let's say I take this one off. Now I got a clique of size 4 here, and I got a clique of size 4 here. I mean, what does it tell you? Like, how do you know the answer is that's a clique of size 5? Yeah, I don't want to go that much deeper into this, but just something for you to think about. There's an algorithm to do this. You can look it up on Wikipedia. There's I guess it's recursive backtracking, brute force-ish algorithm. But yeah, these are two examples of problems where you don't have optimal substructure. And from before, we've seen a lot of problems with optimal substructure. And the hope is that you understand what this what optimal substructure is. Hope you can spot it. And if you have overlapping subproblems and you got optimal substructure, you can solve something using dynamic programming. Okay, so I'm sorry if that was a boring lecture, if I go about this too slowly. It really is not hard, in my opinion. I mean, it's kind of obvious, but students do have problems with optimal substructure. Like, they see the definition and they just don't understand what the definition means. And so here I'm just trying to say, look, it's nothing hard. It's just that if you want to solve a problem, like to find the optimal solution to a problem, you need to have the optimal solution to the subproblems. And in general, most problems you see will have this anyway. So you don't have to worry too much about it. But still, you need to be able to recognize it. And in this unit, I expect you to be able to argue why a problem has an optimal substructure. And you don't have to do that yet. We're going to do that in the next lecture when we're going to go through one example of dynamic programming, and we're going to be doing all this. Right? So I'll see you in the next one.